I guess I didn't get that first part recorded. So after watching the video, what can you tell me what's the difference between weight and mass?
Inertia is mass.
Inertia is mass?
There's mass and narrow inertia.
Okay, Mitch, done. You've had your break. Learning time. What's the difference between weight and mass? Weight changes?
Weight pulls it down and mass is just the other thing.
Big science words, me no understand.
The guy says like weight is gravity's pulling it down. And that's
Well, weight is dependent upon gravity, right? Mass is really just how much stuff, right? How much? No, you're right, absolutely.
So does that mean that like say something weighs a certain amount on or something has a mass, a certain mass on Earth,
Yeah.
but will its mass still be the same on another planet?
Correct.
Or the weight will be different.
Absolutely correct. An object's weight is simply a measure of the force of gravity on the object, and that at that particular instant.
Do you write this down in here?
It's up to you. You need to know this. If you think that writing it down helps you, write it down. If you think just sitting there listening helps you, sit there and listen. Do what you need to do to make you learn this. But having said that, don't just be lazy.
Oh. Thank you.
So an object's weight is simply a measure of the force of gravity on that object at that particular instant. Since weight is a force and gravity is an acceleration, therefore, I think you've seen this already, have you not? I think so, right? Yeah. It's really just F equals ma, right? Fw simply stands for weight force, m is mass, and g is gravitational field strength. And I'll just the greater the mass, the greater the weight, right? Since g remains constant. For example, if I stand on the scale, right? It says about 800, but if I go and grab
It's gonna weigh more.
3 laptops, it's gonna weigh more. How come?
Because you got more weight.
I got more mass.
Yeah.
I gotta lose some weight.
Yeah. Oh, that was bad. Man. That was so bad.
Greater the mass, the greater the weight, since g remains constant. More or less, gravity is 9.8 everywhere on Earth. Now, maybe tomorrow you might discover that gravity is less here in Dauphin.
No.
Acceleration is negative 9.8 ms.
For example, when you stand on a bathroom scale, the scale reads the amount of force that you are exerting on it due to gravity and converts it to mass units. Nobody in here, I'm sure, has a bathroom scale in newtons, just me.
You do.
I do. I don't really know why, but it's cool, fun to play with.
Well, how are you supposed? What's the conversion? What's the conversion?
9.8, right? 9.8 newtons per kilogram.
Divide or multiply?
Divide. So 800 divided by 9.8 will give you my mass in kilos. That's what Lucas is really interested in.
I'm actually ready to go now.
Oh.
According to that, I'm like 242, something like that.
Have you jumped on
I
here?
stepped on there one
Yeah.
day. Yeah. When you weren't looking.
Breaking the rules. You're a rebel. Jumping on your nerd scale. Is this mine?
I don't have one. I borrowed it for a really long time.
So all it really is your bathroom scale is simply measuring a force, but it's converting it, it's calibrated in kilograms, right, or pounds. Most bathroom scales will show both, right? Remember that Newton's second law says that there's an equal and opposite reaction force. The scale exerts an upward force on you. This upward force is known as the normal force, and we've talked a little bit about that as well. It always opposes gravity. Okay, now suppose you're a man in a lovely pair of tan pants and a pink shirt wearing suspenders, and you decide to step on an accelerating elevator. Now the key word here is accelerating. Accelerating means that the net force is Not zero. There is a net force.
Yes.
Right? There is a net force. So you ride the elevator while we're standing on the scale. Since the elevator, and thus the scale, are accelerating you up in the air, they're pushing you up, it must be applying a greater normal force on you, right? If you were unbalanced, okay, so this would be net force 0, right?
Where does that stop the world?
9.
Weight force, normal force, right? But if you're accelerating up, you got a great big giant applied force
Can we sum this up?
pushing you.
'Cause I don't get it.
I'm going to sum it up at the end, right? So your apparent weight force, like the scale is there, right? You have to do what?
You're still gonna have a.
Because you're accelerating up, right?
Push down
You
more.
push down more.
Yeah.
Equal and opposite.
So it's but I thought you have to have more net force. You have to have more net force, but how come it's equal? I don't understand.
Yes, good question. It's because you're accelerating, right? It's equal, and again, it's the scale's applying a force on you. You are applying an equal force on the scale, so you are both accelerating at the same rate. Yeah, I'm kind of splitting hairs here a little bit. I'm getting into some murky waters a little bit. Okay? It must be applying a greater normal force on you. Since you must react with equal and opposite force to keep Newton happy and Mitch, you only
Here.
appear to weigh more. Because the scale does not know the difference, like it's just a stupid old bathroom scale. It doesn't know that it's accelerating you up in the air, right? So it registers more, right?
So I don't actually weigh however much I weigh.
Well, because weight is something that is defined by humans, I mean, some would argue, well, yeah, because your weight is what the scale says, your weight goes up. Others might say, well, your mass hasn't changed, gravity hasn't changed, so your weight is still the same, it's just measuring wrong because you're accelerating. Okay. It is a little bit mind-blowing, isn't it?
Oh yeah, I see that.
Let's sum that up.
What would happen if you were to ride the elevator down? You're at the top of the CN tower, and the elevator just goes away from you. You weigh less, don't you?
Oh, yeah.
Right? And you've all had that feeling.
Yeah.
The top of tall buildings, the elevator pulls away, and you kind of feel that little kind of in your stomach kind of thing, you
That's your
know?
weight kind of like.
Well, it's your stomach staying in place, and the rest of your body moving away from it. That's why you feel that. Or like, you know, if Mitch is cruising down the country road kind of thing, hits a bit of a rise, right?
Shock.
And maybe gets a little air. You ever got a little air, Mitch? Yeah, a little bit.
Yeah, that's some pretty good air.
You kind of get that ooh feeling, right? Roller coaster kind of feeling. Same idea. There are 3 states of motion during a journey in an elevator. Pay attention to each state. We should find out how the net force is related to acceleration. So, the elevator is initially at rest, then it begins to accelerate. Here's the man in the lovely green suit. He's on ground floor.
Is he a banker?
He could be a banker.
Is he gonna lose his jacket earlier? With the pants on.
No, it's a different guy.
Oh, oh.
The elevator is now accelerating, so he feels heavier. He feels heavier. Why does he feel heavier during acceleration?
Can't even see out the windows. He doesn't even have eyes. He's not tall enough to see out the windows. What's he holding? Is it like
The Earth's gravity pulls on the man, right? This is just the man's weight when he's at rest. Normal force exerts a force R on the man, so it's a greater force. In this case, R is greater than mg. By Newton's second law, R minus mg is equal to ma greater than 0. The net force accelerates the man upward. By Newton's third law, the man also exerts a force of magnitude R on the floor of the elevator. And since R is greater than mg, the man becomes heavier, or feels heavier.
Oh,
Now he's the same height, right? How come? Because he's moving at a constant velocity. Once that elevator gets up to speed, do you feel the same? You feel the same. Why? Constant velocity. Because what's happening during constant velocity? No additional net force, right? Why does the man weigh as if he's at rest on the ground?
Because he caught up with himself.
Gravity down. Force up. What's the net force? Zero.
Equals 0 to 60.
Right? Therefore, the net force R minus mg vanishes and the man moves at a constant velocity.
Yeah.
Okay? R equals mg, the man weighs as if he's at rest.
Okay. That wasn't summing it up for me, Mr.
Deceleration. Now,
Trick 6.
when you get to the top of the CN tower, the accelerator, the elevator needs to slow down so that you can stop and get out, right?
Yeah.
Do you weigh less or do you weigh more as you slow down going up?
More.
More.
More. Faster you go, the lighter you are, the slower you go, the heavier.
We've already established that at the bottom, when you step on at the bottom, right, it accelerates you up. At the very start, you sort of buckle your knees. You feel heavy at the start, right? Then constant velocity. Remember, the guy goes like this. Constant velocity, same weight. What happens at the top?
It's heavier again.
Your body tries to keep going due to inertia. The elevator is sort of slowing down, right? You actually weigh less. The man feels lighter. He must have had a Red Bull on the way out.
That was a good one.
You like that? Why does the man feel lighter? In the Earth's gravity pulls on the man, W equals mg. This is just the man's weight when he's at rest. The for the elevator exerts the force R the man, but you'll notice that it is less. Net force R minus mg decelerates the man. By Newton's third law, R is less than mg. The man becomes lighter. All you got to know is that you weigh more at the bottom, and when you go to the top, you weigh less. That's true on the way up. Is it true on the way down? As you pull away from the top floor, what happens? I guess I've gone through them all, right? As you pull away at the top, the floor pulls away underneath you, right? You feel lighter. You always weigh more at the bottom. What about when you're slowing down when you get to the bottom? People have been on an elevator. When you get to the bottom, what happens? Your knees kind of do this, right? You feel heavier? You always weigh more at the bottom.
You always do ever get to the bottom? Not really, because there's another floor for a basement.
Whatever, dude.
He said to get to the bottom.
So, here you weigh more. Does it matter whether you're going up or down? No, you weigh more at the bottom. Put something for you to stand on. When you're slowing down going up or accelerating away, you're going to weigh less. So if you really want to lose weight, all you got to do is
Live in a really tall apartment building.
yeah, and continually go down, right? And never get to the bottom.
And just live in an endless elevator shaft that's always going down.
What do you call that, Mr. Man? Don't close that.
Free falling.
Or just basically go to
All right, let's do some elevator sample weight problem. Sample problem.
example number 5.
Here we go. Example number 5. I don't know why I have this in here. I don't like that one little bit. I don't like that one bit, by the way. Were you? Okay. A man standing in an elevator has a mass of 60 kilograms. What is his weight if the elevator is stopped? Well, as always, we like to start with the easy question. FW equals mg. We're talking weight, not mass. So 60 times 9.8 or 588 newtons. I took 60 times 9.8.
Okay, why are we trying to find his mass?
What is his weight? His weight is not 60 kilograms. That's his mass. That was that whole 3-minute video at the start with the Australian dude.
Is it stopped?
God.
If the elevator stopped, right?
It asks, is it stopped? Is it?
The elevator has stopped.
Yeah, okay. Is it?
What is his weight if the elevator is stopped?
It asks, is it stopped?
No, it says the question mark is for the what is his weight.
I figured we're halfway through it, so I keep going.
B is accelerating upwards from the ground floor at 1.5 meters per second squared. Now, there's a lot of different ways to sort of show your work here. This is the way I'm going to recommend. I'm going to write FAP.
Stop. I like it. That's weird to spell it. What's Bob stand for? Okay, I'm sorry.
Apparent weight force. Apparent.
What's the F for?
Force, right? Because it's a force. Well, because if I said FA, you'd say applied force, right? So it's the apparent weight.
I put PH or something.
pH.
Stop. Sorry. I don't know.
What would you like me to call it, Nate? No, none of those things.
Just that.
Just stop.
All right.
Stop will work.
FAP will work. All right. So what is the weight force? 588. Oh, the mass is 60. Now we're accelerating upwards at 1.5. Is the apparent weight going to be greater in this situation? Yes. So we're going to add it.
How many types of forces do you have to remember?
A gazillion.
What the hell? Like apparent, I've never heard of that until now.
Because I just told you about it.
Well, you expected us to do this question yesterday.
No, he didn't.
Yeah, you attempted.
elevator one.
No, he told
Did you get 1.5 something?
Don't do the elevator one.
Acceleration
So his apparent weight at the bottom, accelerating upwards, is 678 newtons. He weighs more.
Watch out, look at that.
What about C, slowing down at 2 meters per second squared as it approaches the top floor? Same thing.
60 times 1.5, 1.5. Okay. I can't do that. No, just showed me it's not pretty.
This time, I'm going to put a -2 there. Because it's slowing down as you rise up, right? Do you weigh less at the top, slowing down? Yes. Okay. So, don't get too hung up on the signs and everything here. Just make sure that when you're at the top of a big building, that you weigh less than what you do at the start, right? That's the important thing.
We will. Okay, which one's at the bottom? Which one's at the top? Oh, which one's at the bottom? Okay. Here we go. Now you do. Oh.
I would like you to try D and E right here. Go ahead. I've given you the tools. You should be able to do it. Do D and E. Do it in a pencil, and then we can fix it if we need to. Yeah, for D you should have got 480. So that's going to be 588 plus the mass 60. It's going to be minus 1.8 because you weigh less. And E you should have got 678 newtons. Is that what you got?
How do you do that one, Mr. Bennett?
Oh, yeah.
You're slowing down at 1.5, right? So you take the 588 plus mass, 60 times 1.5.
Are we using top?
Yep. Anything at the top, you're going to be weighing less, right?
But when the,
You know what, it really doesn't matter to me here how you do this. I'm kind of fudging things quite a bit here.
You're not
so like,
Yeah.
for each question at the top, you.
Yeah, it's negative, you're right, yeah. It's because if I do it the proper way, it's really confusing, and it makes it way more confusing than it needs to be. You just need to know, at the top, whether you're going up or coming down, it's gonna weigh less, and at the bottom, whether you're going up or coming down, it's gonna weigh more. If I show you the proper sign vector stuff, it's just gonna, your head's gonna explode. Okay. You can now do every single question in this booklet. What I mean by that is, you have the ability to do it. I'm not saying you gotta do them all.
You know which one do you use stop for?
Anytime you're in an elevator, basically. Okay?
So stop at the elevator.
I'm going to insist on only one set of questions. Okay? In this booklet, I'm going to insist on questions 7, 8, and 9. Okay? 7 and 8 and 9. Kyle is flying a helicopter. You must do those ones. Okay? I'm going to be talking about those in the next day or so.
Does that have to do with stop?
It does not.
So we don't
Okay.
do it? We don't do it?
Do them. Don't use the elevator logic that I showed you. Tomorrow we'll deal with gravity. Okay? And then we got to get into some frictional stuff. That is all for today. Do some problems. Don't just sit back and do nothing.
Not even in the elevator.